So my research is primarily in planetary science, and some of you may have seen parts of this before, but I'm assuming that there are enough new fellows that I'm kind of going to make this a flyover of results and not so much a detailed scientific tour of everything I've done. I think the relationship between planetary science and stewardship science is not necessarily an obvious one for many people. And so when I say stewardship science outside the box, really what I'm talking about are ways of looking for interdisciplinary possibilities. Because this is really sort of a theme that I feel like has guided the choices I've made in my research directions. But I also kind of offer this as a theme to encourage the current fellows in ways of thinking about how to apply your research in multiple areas. So as I mentioned, planetary science and astrophysics usually are not really grouped with these themes that are more typically considered stewardship science, but I will argue that they're actually all very closely interrelated, and the place that I've been trying to sort of sit is right at the intersection of all of these areas. So in planetary science, we share a lot of common needs with stewardship science projects. And these include using tools. We need tools to access high pressure temperature states in increasingly controlled ways. And once we get there, we need diagnostics to measure the properties in these states and to characterize them. We also rely heavily on computation, both to model experiments, to model planetary scale events, and also to help with interpretation of results. And really, we're measuring the same properties as many stewardship science problems revolve around. So things like compressibilities, melting and phase relations, transport properties. These are all things that these disciplines have in common. So what I'd like to kind of try to call out as I go through the different opportunities that I've pursued are sort of ways of looking for crossovers between disciplines and ways of looking for dual purpose problems. I think yesterday Matt Gomez made the comment that sometimes basic science is sort of, the whipping boy at these big facilities at the labs. And so I think this is, at least for me, this has been a rewarding way to think about my science and a way to broaden the community that I work with and use a broader array of tools. But I think for you guys also, sort of thinking of your research at these sort of intersections is a valuable way of building basic science into what you're doing, even if it's a more directly programmatic theme. And this is beneficial for lots of reasons, partly because you can appeal to a wider variety of funding opportunities, partly because you can work with a broader array of people, both in and outside the labs, and also because often, even if a primary goal of an experiment doesn't work, if you're thinking about it in this sort of way, you can get secondary results that are interesting to another theme. And also, I'd encourage you to try to think about ways of applying tools to do something completely new. So that's something else that we've tried to do, using these stewardship science tools to do planetary science. Because when I showed up as a grad student, for instance, really no one was using these to do geophysics, and that seemed like a gaping hole and an obvious thing to do. So the physics and chemistry of high pressure are interesting to me for a number of reasons, but especially because when we get to pressures of around 100 GPa or 1 megabar, the PDV work that we're doing on a material is approximately equivalent to the chemical bonding energies of valence electrons. So when you squeeze something to a megabar, really what you're doing is you're starting to affect the way that it bonds, the way that atoms interact with each other. And so really we can access a whole new kind of chemistry at these sorts of pressures. And there are various ways of getting there from, not in a multi-anvil, these go up to sort of the few to maybe 10 GPa range, but certainly in diamond anvil cells you can exceed 1 or even 2, now rarely 3 megabar. Gas guns are used usually in the few GPa all the way up to a few megabar, and then of course the lasers, which you guys have heard a lot about in the last few days. So my path sort of through these various high pressure tools started at UC Berkeley, where I was a grad student, as Tracy mentioned, mostly looking at mineral equations of state using laser driven shocks. So I was using the Omega laser facility and the Janus laser facility. I then went to the CEA, where I switched to looking at diamond anvil cell techniques, and I'll step through each of these in more detail, looking at molecular fluids and learning synchrotron techniques. And really the goals are very much the same, even though the tools are completely different. And currently I'm a postdoc at Harvard with the Origins Initiative in Sarah Stewart's lab, where I'm thinking more of planetary surface problems rather than deep interiors, and using gas guns to study materials at high pressure. So using this broad array of stewardship science tools, I think, is neat in thinking about the end states of planetary evolution, because the missions like the Kepler mission, which just recently, unfortunately, came to an end, have shown us that there are a number of planetary end states. So what I'm showing here are essentially the mass of the planet normalized to the mass of Jupiter. So Earth is way down here. Here's 1 Jupiter mass. Here's 10 Jupiter masses. And this is the date that these planets were announced in the literature. And mostly this slope is an artifact of the fact that it's harder to see small planets. So, those are the ones that are detected last, and techniques had to be improved before we could start seeing things close to Earth mass. But what strikes me about this plot is you can see that there's really almost a continuum of planetary masses out there. And so what this tells us is that the golden rules we think of for planetary evolution in our solar system, of gaseous planets forming far away from their stars and rocky planets forming close in like Earth and Mars, these really probably aren't the golden rules, that our solar system is one possible end state in a whole continuum of end states. So in terms of understanding planetary structure and evolution, we really need to determine what the rules are for how these planets form and how they migrate over their life. And we'd like to know if Earth is actually special or not. It's, as you sort of imagine extrapolating this graph, you can imagine that increasingly we'll be finding a number of Earth mass planets with future missions. Determining where they are and what their properties are and if their structures are different from our Earth is an interesting problem. So that was the focus of my thesis research. And even for the Earth today, there are a number of unknown problems. So the formation of the Earth, we think, involved many large impact events that may have melted and created magma ocean states. So understanding silicate liquids at high pressure and how these materials melt is important for understanding the earliest formation of the Earth. Today, seismologically, we see discontinuities at the core mantle boundary and these sort of blobs and other regions that are not very well understood in what's called the D double prime layer. These may partially be related to melt. They may also be because of compositional effects and other chemistry that we don't yet fully understand. So even in the present day Earth, there's a real need to understand silicate liquids and equations of state of silicates and oxides at these conditions between 1 and 2 megabar approximately. And understanding especially what their transport properties are if we want to understand how heat is exchanged between core and mantle. So for my thesis research, I looked at sort of 3 of the most predominant minerals in the Earth's mantle: MgO, MgSiO3 or Enstatite, and SiO2. And a case in point, this is a phase diagram for MgO showing predictions for melting and some data from laser-heated diamond anvil cell experiments that were seeking to measure the melt curve. And you can see there are 2 sets of experiments that are extremely discrepant. And then a number of calculated melt curves from theory that are also extremely discrepant by the time you get to the depth of the D double prime layer. So this is the core mantle boundary in the Earth. And you can see that the uncertainties in the melting temperatures are over 3,000 degrees between the highest and lowest predictions. So clearly, if we want to understand what's going on there, we need better experimental constraints at these conditions. So as I mentioned before, I used the Janus laser at Lawrence Livermore National Labs, as well as the Omega laser. NIF is also a possibility for future experiments that I'll talk about closer to the end. But amongst these 3 facilities, we can really go from terrestrial interior conditions to giant planetary conditions and even stellar conditions. So what do we actually measure in these experiments? Those of you that do shock experiments will know the Rankine-Hugoniot equations. These are just conservation equations, conservation of mass, momentum, and energy. And so typically what we measure are velocities. So if you have a shock front propagating through a material, you have the shock velocity and also a particle velocity, which is the actual mass velocity behind. And what the Rankine-Hugoniot equations do is they relate the properties, the initial state of the material in front of the shock, to the shocked properties, or the compressed density, pressure, and internal energy. And essentially a qualitative way of thinking about this is that we're measuring the wave properties. We know the conservation equations, and that allows us to solve for the material properties. And you'll notice that these equations define a relationship between pressure and density, which is this blue curve schematically in this diagram. So when you do a given experiment, you land somewhere on this blue curve depending on how hard you drive your shock. But these equations don't tell us anything about the thermal state. They don't give us any temperature information. And actually, temperature turns out to be a really unique way of looking at the properties of these materials. So going back to the case of MgO, one of my first thesis projects was to develop an optical pyrometry system at the Janus facility so that we could measure temperatures to go along with the kinematic shock variables that are traditionally measured, and to attack problems like this, to look at where materials melt at multi-megabar pressures. And so we did decaying shock experiments where we drive a short laser pulse into the back of our sample. We ablate plastic off the back, and sort of in the way that a rocket takes off, that ablation drives a shock wave through the material in an opposite direction. And we're looking at it from the right over here with an interferometer, a VISAR system that you saw a version of yesterday in some of the talks, and also with the pyrometry system to look at the thermal emission from the shock front. And it turns out that looking for phase changes with pyrometry pyrometry turns out to be a sensitive way of looking for phase changes, I should say. It's sort of, you can think of it almost as shock calorimetry, because subtle changes in the intensities of the self-emission often reveal things that the kinematic variables, the shock velocity, doesn't necessarily show you. And in the case of MgO, that was the case. The shock velocity decays smoothly with time because we put in this short laser pulse. But you can see that the thermal emission has structure in it. And this structure tells us that something's going on in these places. And indeed, what we conclude is in the decaying shock experiments, we go up to about 800 GPa, or about 0.8 terapascal, and we decay down. And these sort of subtle changes in slope actually turn out to reveal crossing the melt curve, we believe, in the B2 phase, and also crossing the B1, B2 solid boundary, solid phase transition. The previous gas gun data were down here, but you can see that MgO is an extremely refractory material. The melting curve is likely very high, especially at core mantle boundary pressures, which are down here. So we're favoring the highest interpretations for the melting curves in that previous phase diagram that I showed you. But this also means that these sorts of conditions, sort of 6,000 to 8,000 degrees and 1 to 2 megabar, are extremely difficult to access, certainly in a diamond anvil cell where laser heating techniques get you to about 5,000 degrees if you're really pushing it, and that's extremely difficult to do at a megabar or above. But also with gas gun techniques, which may go to a few megabar. So really, these are sort of a powerful experimental technique to do something new in earth science, but also MgO is a frequently used window in high pressure experiments on Z or other laser experiments. So understanding transport properties and shock properties of this material at these pressures are interesting for a number of stockpile problems as well. And as I said, this helps guide our understanding of what's going on, for instance, at the core mantle boundary in the Earth. So another material that we looked at again was Enstatite, or MgSiO3, which you can think of as just a mixture of MgO and SiO2. And we see similar, but even in this case more pronounced structure in the thermal emission in our decaying shock wave. So we see this big bump. But for the first time, we also saw a simultaneous discontinuity in shock velocity, which you can see here in the raw data with where the arrows are. This discontinuity in velocity suggests that there's a volume change going on in the material. The temperature tells us that there's an energetic change going on. So we can put these together to identify what turned out to be a very new kind of phase transformation. So I did experiments on two different polymorphs, both a single crystal, so this is the single crystal Hugonio shown in this greenish color, as well as a glass, so an amorphous starting material. So it's the same composition, but different initial densities. And if you got a glance at those Hugonio equations, you saw that the rho naught was in there, the initial density. That determines the end state you achieve. So if we do similar experiments with different initial densities, we trace different paths in pressure temperature space. And we see that same kind of discontinuity in the thermal emission and the velocity in both polymorphs, but in the glass, it occurs at much, much higher temperatures and pressures. So we believe we're seeing the same transition in both materials. And we've concluded that this is likely a transition between a low-density liquid phase and a high-density liquid phase. And this is the first observation of a transition like this using decaying shocks. This is interesting for a number of reasons. One, because it tells us that there's still complex chemistry going on in these materials at these extreme conditions. And this is something that I think many people don't necessarily expect. They think that at above an EV in temperature and 3 megabar, you're starting to really smear things out, and there's not a whole lot going on. You're in this sort of liquid state where you're maybe starting to dissociate. And this tells us that, in fact, for extrasolar planetary interiors, this kind of transition may be interesting. And these sorts of transitions have been predicted in a number of other materials. They've been observed in phosphorus at much, much lower pressures. Now, recently in cesium, a first-order liquid-liquid transition has been predicted in nitrogen. And you can think of, in some ways, the hydrogen plasma phase transition as an analogous transition. This sort of transition is important in the sort of magma ocean stage of early planets. If you have low-density liquid and high-density liquid, you can think of the effect of these wanting to separate and entrain other elements with them. So this is potentially a way of partitioning other chemical elements very efficiently and relatively rapidly in the earliest stages of planetary evolution. We also measure the reflectivities of the shock fronts, and this gives us information about conductivities, electrical DC conductivities and thermal conductivities. And what we find out is that all of these minerals, quartz, MgO, and MgSiO3, all start behaving like poor metals in the liquid state, which has implications for the magnetic fields of extrasolar planets. If these materials can actually act like poor metals, you might not actually need, they could potentially participate in the formation of magnetic fields without requiring convecting liquid iron, which is the way we typically think of magnetic field generation in the Earth. So this sort of paints a very different picture of extrasolar planets and their potential structure and behavior. So this really got me interested in delving deeper into high-pressure chemistry, and that motivated my shift to my first postdoc at the CEA in France. As I mentioned, some of these sorts of liquid-liquid transitions have been predicted in molecular fluids, things like pure N2. But molecular systems are also important for giant planetary interiors, planets like Uranus and Neptune. I was also interested in sort of broadening my toolbox and learning to use diamond anvil cell techniques because I think we've heard the expression before, when all you have is a hammer, sort of everything looks like a nail, right? And when you do laser-driven shock experiments and that's your only tool, it's sort of like trying to take something apart with a hammer. You bash it and you see what comes out. It's not a very subtle or refined way of looking at the detailed chemistry of what's going on. Whereas in the diamond anvil cell, you can really make detailed studies of the chemistry. You can do all kinds of spectroscopy that are not possible yet for these laser-driven shock experiments. So we can do much more detailed studies on materials over long periods of time. So I thought I'd include a little bit about sort of the experience of being at the CEA and choosing to go abroad for a postdoc. For me, this was a really valuable opportunity, both sort of culturally and scientifically. But I would say, if anyone wants to ask me questions about it, you're welcome. It worked out for me because I'd already spent 2 years in a Francophone country, so I spoke French before I got there, and that turned out to be absolutely invaluable because everything is conducted in French in the site where I work. The seminars, the group meetings, that's just how it works. And so if I had not spoken French before I got there, I think I would have been miserable. There are other CEA sites that have more international people. Some of you may know Angelo Signoracci, who is also an SSGF fellow, who went to work at number 2 here. I was at number 7. CEA has multiple sites around France. The site where he's working is much more open. There's a lot more sort of international influence, a lot more English spoken. But I think even he's learning a lot of French at the same time. So I also worked with a group that I'd been collaborating with as a graduate student. So I also had a very good idea of where I was going and what I was getting into. And my advisor at the CEA also had a good idea of where I was coming from. And I would say that was also an extremely important factor in making this a good experience for me. There are definitely good and bad aspects of working in a French national lab. The place where I worked is essentially the French Los Alamos. So it's high security. I was the foreign national, which was an interesting experience. It meant that I had very limited mobility in some sense. which wasn't necessarily a hindrance for what I wanted to do. But it does sort of put it in a different perspective when you're the one who's not allowed to leave your building, or who has to ask permission for every other movement. The choice of projects in the French labs is generally much more constrained or even predetermined when you get there. I was lucky again in that I knew the person that I was going to be working with, so I was able to negotiate for what I wanted to do. But many postdocs that come from French PhDs will arrive and be told that this is what you're going to study. And so that's something, if you're thinking of going abroad, I would caution that you make sure you know what you're going to be able to do ahead of time. And as I say, for me, that worked out well. I think for Angelo as well, but I do know people that have gone to France and been sort of shocked that they were assigned something. The work schedules are very different. The French are religious about the 35-hour work week, but that doesn't actually work for most people. You can't get that much done in a short work day, so people end up spending extra time, and there are complicated ways that this is compensated for. But the working hours were very strictly enforced, and that was something that was difficult to adjust to for me. There's a lot more sort of hierarchical structure as well. As a postdoc, you might not necessarily be as visible or have as much contact with sort of senior management as you will in the labs here. And that's just sort of the culture of the labs. It's not necessarily a bad thing because for me, it meant that I was sort of able to stay in my corner and I didn't have to think about those things, and I was able to do my science without much other interruption. I didn't actually have to stick up for my own funding or defend my own projects very much to the management in our department, which was nice for me because I could just sort of do my thing, and it was very self-paced. The positives are that this is really a great opportunity to broaden your community and to see parallel efforts on large projects. At Site 10 here near Bordeaux, this is where the French are building the Laser Mégajoule, which is the equivalent of NIF, essentially. It's not quite the same facility, but it's very close. It was really interesting for me to sort of be a fly on the wall within the community that's working on that facility, knowing what's going on at Livermore, and sort of being able to compare and contrast the way that these projects are being done. That gave me a very interesting perspective. It's also a great opportunity to develop collaborations that you can carry forward and develop familiarity with other groups. I was trying to find other pictures of the CEA to give you an idea what it looks like. This chateau is actually in the middle of the lab site where I worked. This was the first building that became ultimately the lab. And unfortunately, they didn't maintain this architectural style for the rest of the buildings. The rest of it was built in mostly the 60s and 70s out of concrete and has very much that National Lab aura to it. But it was nice to walk past this building every day and think about what it was like in the very beginning. Another plus is that you have opportunities to travel. And so I made it a point to sample as much as I could. So the projects that I worked on in France, again, was a pretty big shift from the mineralogical equations of state that I was doing as a grad student. Here I was looking at chemistry and molecular mixtures. This is interesting because at high pressure you can actually form whole new compounds called van der Waals compounds, where you have molecules essentially assuming a solid crystalline structure and interacting very weakly with each other. So they're still in molecular form. In this case, nitrogen is still triple bonded, but you can actually form a lattice of a compound of nitrogen and helium. And so this is a crystal of nitrogen and helium together. The same is true for xenon and oxygen, for instance. And xenon, being a noble gas, is not something you think of easily being able to bond with other things. But to go back to my point about chemistry being different at high pressure, I think this is a great example of these high pressure compounds that you can really only get to, but that have interesting properties. So this is a sort of generalized phase diagram for molecular fluids from Chungshik-Yu, showing the kinds of transitions that are predicted for many of these sorts of systems. So they may undergo solid-solid transitions in the same way the minerals do. They may undergo liquid-liquid transitions, which is one thing we were interested in. They may polymerize, which is interesting from an energetic standpoint, especially in the case of nitrogen, which has been found to turn into a polymeric form at very high pressure and be extremely exothermic in going back to the diatomic form. This is a really unique means of probing interatomic bonding, because in the diamond anvil cell you can perturb the pressure just a little bit, And you can do, as I mentioned, all kinds of spectroscopy to look at vibrational properties. You can throw in a little bit of something else to dope your sample and see how that affects the vibrational properties. So it's a very direct and simple way of sort of, stretching and perturbing the way that your molecules are behaving. And you can actually do very fine scale measurements, which is one of the things that attracted me. So again, they display very subtle and complex chemistry, as this phase diagram suggests. You can make these van der Waals compounds. These are common reaction products in high PT chemistry. So from a stockpile stewardship point of view, it's interesting to understand the chemistry of hydrogen, carbon, nitrogen, oxygen systems at high pressure. And as I mentioned, from a planetary standpoint, the equations of state of these materials are important. So one of my sort of long-term projects when I was there was looking at the binary phase diagram of nitrogen and hydrogen, and measuring specifically the melting curve as a function of composition. So this is hydrogen composition, but also looking for these sorts of van der Waals compounds. And we actually found two in this phase diagram. This is a single crystal of N26H27, which has this interesting structure. You can see it's a rhombohedral structure. So this is a nitrogen-hydrogen alloy, essentially. And the hydrogens are contained in these sort of tubes of nitrogen. So these bluish violet-colored molecules are the nitrogen, these little dumbbells. And each of these is actually an H2 molecule, the gray. So the interesting thing about this structure is, I'm sure most of you know that the search for the metallization of hydrogen is a sort of a holy grail in condensed matter physics. And ways of sort of lowering the thresholds for metallization in these materials are of extreme interest to a lot of people. The idea is that in a structure like this, if you can find structures like this that you can then compress, you can squeeze the hydrogen together by confinement in another lattice of something else. Other applications for these sorts of materials might include ultimately hydrogen storage, if you can come up with a way of stabilizing and recovering these at ambient pressure. And as I mentioned, this polymeric form of nitrogen is one thing that people are interested in recovering at low pressure. But you have to find ways of keeping it in that polymeric form, and doping it with hydrogen is one way that you might do that. You might sort of passivate the ends of these polymers so that you can make it at high pressure but get it back when you decompress. The other solid we found in this experiment was this cubic structure, which is just N2H2 twice. And I have to say that growing these crystals in the diamond cell is probably one of the most fun things that I've ever done in the lab, because you change the pressure in the diamond anvil cell with an inflatable metallic membrane. The diamonds are here in the center. And so essentially you have a pressure regulator, and you can turn the pressure up and down on the pressure regulator to increase the pressure and grow your crystal, or decrease it and shrink it. So you can kind of sit there with your hand on the knob and watch the crystal do this under the microscope. It's really challenging, actually, to get a single crystal like this. It took a lot of practice, but once you have them, you can do all kinds of interesting studies at the synchrotron, for instance, which is where we measured this structure by doing single crystal diffraction on a crystal like this one. There are a number of other synchrotron applications that are of obvious interest to stewardship science in the diamond anvil cell as well, but I'm just focusing on these molecular systems. These are challenging systems because they're low Z. These are light elements. So getting a lot of sufficient X-ray scattering to solve a structure like this is not very easy. The other problem that I worked on was methane. Methane is also a detonation product, but as the sort of the most fundamental hydrocarbon, it's interesting to understand this equation of state. The melting curve of methane was not known beyond a few GPa, surprisingly, at high pressure. So one of the things that I spent a lot of time doing was developing ways of looking at methane at high temperature and doing simultaneous spectroscopy. It's easy, actually, to do melting experiments if you can heat the sample uniformly. So one of the things I did was work on resistive heating techniques, where we wrap the gasket of our diamond cell with what looks like a little stovetop, basically, and this gets folded over both sides of the gasket so that we can heat the circumference of the gasket and consequently heat the sample, which is right in between the two diamonds here. And you can actually follow the melting curve by staying in this coexistence region. So this is a ruby that we use for ruby fluorescence to measure the pressure. This is a big chunk of samarium, which was supposed to be on the side of the gasket but drifted in. And so by just visually observing this coexistence and measuring the temperature, you can slowly march your way up. So my data are these green points. up to about 10 GPa. We also wanted to do laser heating experiments. It's not immediately evident how you do laser heating experiments on a transparent fluid like this, or transparent solid, because it's not very absorbing to most of the typical laser wavelengths that are used for heating experiments in the diamond anvil cell. So one of the things that we're working on is developing techniques to put couplers that are chemically inert in the sample. So what you see here is the edge of the gasket, and this sort of reticulated pattern is solid methane, and this is boron-doped diamond little donut that we make with a focused ion beam. So the idea is that we contain the hot methane within the sort of the center of the donut here. We can do spectroscopy and measure temperature by means of pyrometry right at that spot. This black spot you see is actually the field of view of the pyrometer. And we can generate a uniform temperature distribution around the sample where we're actually making the measurement. Because one of the big problems in laser-heated diamond anvil cell experiments is that you tend to have large temperature gradients. And unless you really know what part of your sample you're probing, you're probably not at your temperature maximum, or you're at some part of this Gaussian beam profile. You also have material tending to move away from the hot spot within your sample chamber. So this is a challenging thing to do. You want to both confine the sample, as we're trying to do with these little donuts, but also create a uniform temperature distribution. The other advantage is that we can take this to the synchrotron and we can look at properties like liquid structure factor. So this is another thing we spent a lot of time doing, implementing this solar slit array to reduce the background. The problem with trying to do diffraction on these very low Z materials is that you have a huge Compton background from the diamond anvils themselves, because they're usually many, many tens of times thicker than your sample. Your sample may be on the order of 10 microns thick in between the diamonds, but you've got up to a millimeter of diamond on either side. And what these slits do is they basically serve as sort of a spatial filter to limit the diffracting volume that the detector sees. So we couple this with the resistively heated diamond cell so that we can look at coordination changes in these low Z molecular fluids and step up in pressure and temperature in the fluid state and look at how that coordination changes. You can see the difference without this solar slit array. We have this huge background shown in red. With it, we can actually start picking out the second coordination peaks in argon. And we pushed this to hydrogen, which is sort of the ultimate test because it's the lightest and hardest element to get any signal from. And this data is still pretty crummy, but it shows there is a peak, which is sort of the encouraging thing. And we see the peak evolving in pressure. So this was good proof of concept that we can actually apply this technique and look at coordination changes in chemistry in these liquids to start looking for these complex or more subtle liquid transitions. So I'll talk very quickly about a way of combining tools for another problem in planetary science. And this is sort of combining the diamond anvil cell methods that I used in my postdoc and the laser-driven shock methods that I used in my thesis to look at the interiors of Jupiter and Saturn. These are predominantly hydrogen and helium planets, but the equations of state of these materials really determine the structure. So what I'm showing here is a paper from Didier Saumon where he predicts the mass of the heavy element mass, essentially, trying to look at what the possible core size might be in these planets by picking different equations of state for helium. You can see that the equation of state you choose gives you these different possible phase spaces for what the heavy element composition is in these planets, and that there's an extremely wide range. So you really need to know the helium equation of state in order to say something about the structure of these planets. The other question is, are hydrogen and helium miscible at these high pressures? There are predictions that show that there should be this immiscibility region. These are the planetary isotopes in temperature and pressure, and sorry, that's a little small. So by combining laser-driven shocks and the diamond anvil cells, we can get to these conditions and we can try to answer the questions about whether they phase separate. There's this problem that Saturn seems to have a luminosity that's higher than it should be for the age of the planet. So that seems to point to there being some kind of energy source in the planet that we don't understand. And separation of hydrogen and helium might help explain that. Probably not by itself, but it may be one important mechanism. So this was really a collaboration between the group at Berkeley where I did my thesis and the group at CEA where I did my postdoc. And what we do is we pre-compress a sample of either hydrogen or helium or mixtures in a modified diamond anvil cell where the back diamond is actually a thin plate rather than a brilliant cut diamond like this. We either directly drive the back of that diamond sample with lasers. This is at the Omega facility, or in some cases with a gold half-ROM. I think everyone here is familiar with the whole ROM idea. We call this a half-ROM because it's a whole ROM cut in two. And that can serve as a sort of more uniform drive. So sort of zooming in on the sample region, we have our fluid sample pre-compressed to some pressure. Again, that initial density, the rho naught in the Hugoniot equations is important. So being able to tune the initial density means that we can tune the phase space that we end up in. So what I'm showing here is the final compressed density over the initial density, and you can see that as we increase the initial density, we can access this space between the Hugoniot and the isentrope in pressure density or pressure temperature space. So this is a really nice method to be able to sort of fine-tune where you're going to end up with your shock instead of just landing on that principal Hugoniot, that blue curve I showed you in the beginning of the talk. This is a picture of one of the diamond cells getting shot at Omega. We use quartz as a standard material to impedance match. And again, there's a ruby that we use to measure the initial pressure in the sample. So in this case, this is about 400 microns in diameter or so. So our collaboration looked at a number of different pre-compressions for a 50-50 mixture, 0.4, 2, and 4 GPa. And you can see that as we change the pre-compression from 0.4 GPa to 4 GPa, what we're doing is we're getting to higher pressures at the same temperature. And so that's really interesting because that allows us to come over to this part of phase space where we're starting to actually cross the planetary isentropes. So these experiments at the lowest temperatures and higher pressure end are directly accessing planetary interior conditions. And these colors here are sort of schematically showing where the red and the blue fall in Saturn and Jupiter. So you can see that in Jupiter, we're still sort of just scratching the surface because it's a huge planet. The core is somewhere around 40 megabar probably. But in Saturn, we're getting down into this interesting region where we might be able to address these demixing problems. So with higher pre-compression, we get to cooler temperatures and deeper planetary conditions. So we've also looked at 20% mixtures, and we can compare our data, the Hugonios essentially, to sort of what's predicted by simple sort of kind of linear mixing models. And we can see if there's any compositional effect by looking at a 20% versus 50% mixture. And what you can see is that the 20% mixtures deviate both in temperature and in volume, essentially, P rho, from what this sort of simple linear mixing model predicts. And the reflectivities are also quite different. You expect, sorry, this doesn't show up very well, but the arrows here sort of show you what we pick out as the demixing region. We take this deviation in temperature and volume to be signs that the materials are actually separating. And indeed here, you expect the most reflective component, if they're separating, to dominate your reflectivity measurement. So if they're separating, we expect to measure predominantly the reflectivity of hydrogen, which is what we measure between about 0.4 and about 0.8 EV in temperature. So this gives us both pressure bounds as well as temperature bounds for where these materials might be demixing for a given composition. And so indeed we can put limits on where this demixing is occurring relative to the planetary isentropes and compare to predictions. And what we see is that the ab initio models are probably underestimating the gap energy because they're predicting that these materials become metallic sooner than they do. And it turns out that insulator metal transition is probably what's dictating the solubility. These are difficult things to take into account in calculations, which is why the experiments are valuable in this case. And what we conclude is that most of Jupiter's isentrope is actually falls within this demixing region, and Saturn's almost entirely within it. So this might contribute partly to Saturn's excess luminosity. It could also possibly explain the fact that we see less helium in Jupiter's atmosphere than would be expected. So finally, the last stop on this sort of whirlwind tour is where I am now. And again, I said that looking for these sort of interdisciplinary possibilities has been sort of a strong guiding choice in what I've done. At Harvard, they have what's called the Origins of Life Initiative, which brings together people from geoscience, astronomy, the Center for Astrophysics, biology, chemistry, and it really encourages people from these different departments to work together towards common research goals, in this case, things having to do with the origin of life. And looking at problems like what are the ingredients for a habitable planet? How do you make a planet initially? How does that planet evolve? People at the CFA, for instance, are heavily involved with the Kepler mission in finding these extrasolar planets and determining that continuum of planetary end states that I showed you at the beginning. So the Origins Initiative is really, to me, a great opportunity to be able to work with people in lots of different areas and to be able to sort of coax them into thinking about these high pressure processes, but also to be able to take advantage of their expertise to design and think about different projects that aren't traditionally thought of in the shock physics realm. So the problems I'm trying to address here are looking at aqueous mineralogy on Mars and the history of clay minerals, particularly how you squeeze out volatiles when you form a crater, for instance, and these are shock compressed. There are a lot of minerals like montmorillonite and nantronite, which Rick Krauss has looked at, that are detected on Mars remotely by orbiting satellites. And one of the things that Rick has found is that the spectral signatures of these clays change under shock compression, so you might not recognize them as a clay if they're shocked. So it's important, on the one hand, to interpret mineralogical observations of the surface of Mars. It's also important for understanding the history of water. Finally, I'm interested in looking at shock-induced chemistry. Some of you might know Nir Goldman at Livermore. He recently published a paper about shock-induced chemistry from meteorite impacts, looking at, again, these simple molecular systems and ways of using shocks to overcome reaction barriers and look at how geological ingredients in the early Earth history finally gave way to the precursors of biology, how you can make these simple prebiotic molecules. We do gas gun experiments at Harvard, so this is sort of like what you saw yesterday for Z, the before and the after picture. This is the gas gun in Sarah Stewart's lab, and we can, again, measure equations of state. And we're working toward controlled recovery experiments to look at the devolatilization and shock chemistry. And the final tool that I'm adding to my toolbox at Harvard is computation, which is something that I've not delved very deeply into yet. Sarah uses computation to look at everything from these sort of moon-forming planetary scale impacts. So this is a Mars-sized impactor hitting the early Earth, which is rapidly rotating. And you're tracing the particles to see how much of this material gets incorporated into the Earth versus how much gets sprayed out. You can also look at cratering, and the goal is to input accurate equations of state into these models so that you can take the high pressure equations of state I've been talking about and inform what's actually going on, in this case with cratering and icy materials. This is more of Sarah's work. And finally, I'm starting to use these tools to design recovery capsules and to help with my experiments on the gun. Because this is a valuable way of predicting what's going to happen when we have a flyer impacting a capsule with a sample in the middle. So kind of, if you're at the labs, you know about lessons learned. I kind of use this in a tongue-in-cheek way, and that the lessons I've learned are ways of looking for overlap in research opportunities. Has been a really rewarding way of kind of thinking about crossing these different boundaries and using these stewardship science tools in a way that I think a lot of people don't necessarily think of them. Again, I would encourage everyone to try to attack problems at the boundaries of your discipline, like using facilities like this for geophysics and thinking of ways of building in basic science to your current work, partly because it expands the number of people you can work with, but also because it's a rewarding way of attacking new problems and actually sort of finding new inspiration. The one thing I would caution is to sort of be aware of breadth versus depth. There's such a thing as being sort of a jack of all trades and master of none, and I think I'm kind of towing the line on that balance by trying to use all these different tools, but at the same time, it's been a very rewarding opportunity. So, thanks.